Hi, I'm Josephine and this is Peter, and for our final project we decided to use an unscented Kalman filter to localize a robot in a Chilean mine. The motivation behind this project is that the mining industry is making a move towards autonomy, which has a lot of potential to improve safety and working conditions and increase productivity. Mines are a challenging environment for robotics because they're dimly lit and GPS limited, so we thought this would be an interesting project to take on. So we're using our unscented Kalman filter to estimate the robot's pose, which is its x and y position in a global frame, and its heading theta. In order to predict the robot's pose, we use encoder data, which takes the form of the distance traveled by the left and right wheels at each time step. Then we correct that prediction using the LiDAR data. The LiDAR data takes the form of many different LiDAR beams, each of which has an associated range and azimuth, which are given in the Z and theta Z matrices. Lastly, we have associated covariance matrices for both the LiDAR beams and the encoder data, which are given by QT and RT, and which are used to calculate covariance matrices in our UK. The data that we're using comes from the open source Chilean mine dataset and includes 3D LiDAR data and wheel encoder data. The 3D LiDAR performs low-resolution scans as it moves, and then stops at 44 locations to perform high-resolution scans, which we can use as truth locations. The low-resolution scans are performed as a LiDAR rotates very slowly, so that one 360-degree scan is performed every 6 seconds. Additionally, we have a 2D map of the tunnels, which we can basically use as an occupancy grid, and this allows us to perform LiDAR scan matching in our correction step. In order to use the LiDAR data, we need to filter it first. So we started by compressing the data from 3 dimensions to 2 dimensions since we're only concerned with 2-dimensional localization. Then we converted these XY points into a range and an azimuth, and converted them from the LiDAR's frame into the robot's frame. Then we still had a bunch of different beams at each time step. So we took all of those beams and split them into 5 different chunks of beams. And then for each chunk, we found the mu and the associated variance, which is what we use in our Q matrix.
So here's the block diagram of our unscented Kalman filter. As mentioned before, the prediction step takes in the left and right encoder deltas, and the correction step takes in the LiDAR measurements, the range, the azimuth, which we use for our expected measurement calculation, and a covariance. And so we correct every 2 seconds. A scan of 360 degrees takes 6 seconds. And we felt in 6 seconds we move a fair amount of distance. So we only use 1/3 of a scan, which means we correct every 2 seconds. We thought since we're moving slow enough, a partial scan was more appropriate. Here's our measurement model. So when we calculated the average beams, we also calculated the average azimuth for all of these beams. So our measurement model takes in a azimuth and it calculates the expected distance based on our map. And we do this just by drawing a line using y equals mx plus b. And so we do this every 2 to 3 seconds. Measurements being plotted, we're plotting 1/3 of a scan at a time. You can see this one is a good match, but if the calculated angle is slightly off, then we have a bad match. We see this is another good match, so it's a good correction, but then we propagate this potential for like a bad correction step like this one. Generally we get good corrections looking backwards and not as good ones looking forwards.
So for our experiment, we simulated the robot's movement from point A to point C on the map. So here we have plots of the robot's path for both an unscented Kalman filter and a particle filter, because we wanted to kind of compare their performances and see which one would work better. For the known pose path, we just drew straight lines between known poses. We didn't have access to the actual path, so this is just an estimate, but we think it's a pretty reasonable one. You can see that the unscented Kalman filters seem to perform a lot better for the first 100 meters because it kind of zigzags less and sticks closer to the known path, whereas a particle filter is kind of all over the place. We calculated the path tracking error for both filters and put that into an RMSE, and you can see that the particle filter actually has a slightly lower RMSE, which is surprising given that it seemed to zigzag a lot more. But we think that this is due to some kind of error in our path estimation because we assumed that the robot in its true path moved at constant velocity, and this might not be true. So the unscented Kalman filter was ahead or below of where it should have been according to the truth measurements, and it might actually have been performing a lot better than that. But you can see that both the unscented Kalman filter and particle filter match up in their residuals. So the three peaks that you can see in the unscented Kalman filter are from the three intersections that the robot encounters here at A, B, and at about 100 meters. So it gets really lost around these intersections and then seems to find itself again.
So here are the plots of the estimated state of the robot from points A to C, and we see that the unscented Kalman filter gets off track. It tracks really nicely up to about 100 meters, and then after that things go haywire. Whereas the particle filter, which we implemented second, seems to be able to track the state relatively well. And so we conclude that maximizing filter performance requires balancing the number of scans with the frequency of correction, because we were correcting every 2 seconds, and when we were zooming in on the data, you can see the estimates jumping a little bit because you're integrating for 2 seconds and then you're correcting. So it's a discontinuous path. You get really zoomed in. Our second conclusion is it's hard to get good results with bad data. The LiDAR is an older LiDAR, and it just doesn't provide a whole lot of information. Like, we couldn't do full-fledged scan matching. It was more just like comparing a couple beams. And for some applications, the particle filter can be better. Any questions?